But see,
People?
you know, to see the results.
Oh.
This is the paper we're going over, and so we're this is the results. The facial tracking on this is pretty impressive, and they're doing it with one freaking camera, no markers, one camera. So if you're just joining, which you are because we just started, we're going to do Chop Talk 371 today, and I'm just getting set up. So hold on, hold everything while I adjust things. And I was just showing Kelly here, who I don't think has seen the results, the video that goes along with this paper. I think most people, especially seeing that the group who are attending, have seen the video that goes along with this paper. If you haven't, just go to Google and look up the paper's title, Reconstructing Detailed Facial or Face Geometry from Monocular Video, and click on the movie link. And you can see the results of this. We went over it last time, and since there's a lot to go through today, we're going to zip right into this. So, dun-dun-dun, Chop Talk 371, Reconstructing. This one is fading fast, so we're just going to bail on that. Face geometry from monocular video. And I'm going to actually spend the time to write down monocular video because it's important. Last time, we talked about the basic concept of this paper, and we talked about how the authors started out with creating a blend shape of model of their face. So I'll pause this because it's distracting. So the very first step in all of this is to have your subject, your fully blown person, sitting in front of two cameras. And we take a stereo pair of this. Using a previous paper written by one of the co-authors on this paper, we generate a 3D scan of your person. We also have a generic blend shape model, which I'm going to draw like this, where we have a neutral pose plus eyebrow up, and alphas on each one of those are actually betas. Typically there's a beta 1, beta or 0, 1, 2, and so on. So we have a generic blend shape model created by artists, rig, of a very generic face. This gets merged into this. Magic happens, which we talked about last time, and out pops out a personalized, the magic here is a Laplacian mesh deformation, personalized blend shape rig. So, what does this mean? And I wanted to really back up a moment and say, hey, look, we've got a blend shape rig that was created by an artist that represents everybody. It is a generic face that can make typical expressions. They have 78 different blend shapes in here, so there's 78 different weights. And this thing can open its mouth, it can raise its eyebrows, it can smile, it can frown, it can do a whole bunch of things. But of course, this person doesn't move exactly the same way as a generic person does. And this step is basically to take this blend shape rig and bend it so that it at least looks, it has the overall shape of this guy. So if the nose on this is a little bit small, the nose gets expanded to fill this guy's face because he has a bigger nose, and the shape of the brow gets, the jaw gets changed to fit the shape of the jaw. But this is a personalized blend shape rig that is kind of, you know, still very, very generic. And won't actually capture the actual motion of this guy's face if you just moved it. It's not the way this guy or gal would move their face. So that's what the rest of the paper is about. They say, okay, we've got this. And we've got a single monocular camera looking at this, our actor here. How do we make this thing move and look like the person we're actually recording? And I just looked, I really want to stress this. This is actually a really tricky thing because all we're doing is now, this guy is animating, you know, there's animation going on here, time is animating, and we are watching this person with one camera. So the only time we were using stereo is to get this initial 3D scan to personalize the blend shape rig. After we're done with that, we're done. We no more stereo. We're trapped in monocular line. So that means that when I get the image out of my camera, all I have is 2D information here. I just have pixel values of pixels of this guy. So you can kind of see what the problem is going to have to be. Not only do we have to, what we want to do is sort of take this blend shape rig and make it move like this guy is moving. But first of all, we have to figure out where his face is in here, right? And then we have to figure out how these pixels that we've got are moving. And then not only that, we have to then make the blend shape rig start moving like that. And then there's still the genericness of this blend shape rig, right? The blend shape rig is kind of in the right shape, but it doesn't really capture the details of this. So how do we take the image stuff that's going on here and deform the blend shape rig so that it actually looks like this guy? That's what we're going to do today. It's going to be fun. All right, so that was last week. We talked about this. So now we are going to jump ahead to section 5. 2D facial feature tracking. So step 1, this is section, well, we'll call it, in case you're following along in the paper, 5.1. Sparse feature tracking. Oops. Now, this is actually kind of fun. This is a fun part of the paper, mostly because we already covered it in a chalk talk. One of the things that we want to do is basically figure out where uniquely identifiable points on this guy's face, or gal's face, is in the image. We want to find the 2D location. So let's draw this a little bit more carefully. Just slightly more carefully. I don't want to take too much time. There's eye, eyebrow, a little bit of nose, we've got a bit of nostril, lip corners over here. There. With that, that is one weird face. So there are things on this face that we can fairly accurately identify. There's the corners of the eyes. Corners of the eyes are great. We can usually pick those guys out. We can pick out points on the nose. There's some definite points there. There's the bridge of the nose. That's actually fairly, if you were given a photograph of a person and you were asked to identify these things, you would actually be able to do this. You'd be able to take your mouse and click on the bottom of the lip and that kind of stuff, that the beginning of the eyebrow, where the eyebrow is the highest point on the eyebrow, you know, various things. You'd be able to identify a good chunk of points without much ambiguity, right? And in fact, these facial feature identifiers are even so good as to even put points along the silhouette of the jawline relatively nicely uniformly distributed as the jaw moves. So that point on there, even as the jaw opens up and down, will pretty much stay on that point on the face. Now, in Chalk Talk about a year ago, or about 6 months ago, we talked about a machine learning way of doing this. And this paper actually has a different way of doing it, but quite frankly, it doesn't really matter. you can use whatever technique you want in order to do this. And we're just going to quickly go over the one in the paper. So the tracking algorithm is based on a 3D point distribution model, which linearly models non-rigid shape variations around this 3D reference location, blah, blah, blah. Well, there's an equation, and I'm going to write it down, and it may look a little scary, but it's not that bad. X, so T, comma, I. So the 2D location of one of those red dots here is equal to, what is that equal to? Well, let's assume that we knew the 3D location of that dot. Well, that 3D location of the dot is going to get scaled, it's going to get projected, it's going to get rotated, and here's the 3D, and let's put this, I'm going to put little hats on this to say that that's a capital X, so I, plus, yeah, I'll write it in here. Plus T, oh, right, plus T. Plus T, or T is a hat. Okay, so look back, you're looking at that and you're going, what? So this is actually kind of a cool thing. You have non-rigid shape variations around a set of 3D reference locations. So what does that mean? Well, this, say we're looking at the point on the corner of that eye. That's I equals 7. Let's say that is that corner of the eye. So we have a generic face, right? We have a generic face, and we have a sort of idea of where that point should be on the generic face in world coordinates, right? But people have different faces. People move their faces. All sorts of things go onto the face. So what happens to this point is this point will start moving through world space based on how the person looks. You know, a generic face, well, somebody of the generic face may have the 3D point of that corner of the eye at one point in world space. But if I substituted my face with somebody else's face, that point might move slightly in world space, right? And also, as your face moves, this thing moves up and down. So that is, look at what we're doing. We're taking this sort of standard location for that corner of the eye, and we're adding something to it. And this adding something to it is interesting. It's cool. This is a 27, I think they use 24 element vector that is basically parameters on this something that we're adding to this location. And this is a matrix. It's a 3 by 24 element matrix. That we have carefully calculated, given a whole bunch of input data. So what this thing does is, this is a thing that basically is, we've basically taken the variability of the location of that point, given different appearances and different facial expressions, and encoded it into a cloud, right? We took that cloud and we did all sorts of stuff, and we said, look, this point, based on appearance and facial expression, moves around in a certain way. And we did that with all these points. And we did a little bit of analysis, and we noticed that there was a set of 24 parameters that kind of let us move through this cloud of points based on appearance and expression and all sorts of stuff. And if you took this set of 24 parameters that kind of described what was going on and multiplied it by this matrix, and there's one matrix like this for every one of these points in here, out popped a 3-element displacement vector, right? So this 3-element displacement vector gets added to this and says, all right, given the description of the appearance and the expression that we've kind of squished into 24 values here, with that description, you get a displacement out of here. All right? So now you kind of see what's going on here, right? we have the point that we're looking for. This is the location of the corner of the eye. And we have an idea of where that corner of the eye should be. But we don't know this. This is scale, projection, and rotation. And we don't know the appearance and expression of the face. But we have these carefully constructed matrices that we built up by looking at a lot of different people's faces in a lot of different expressions that allow us to sort of determine this. So there's a very cool paper by Sarag in 2011, which came up with a way of solving this given a certain amount of input, given an image, basically. And what it does is it starts adjusting this parameter and adjusting that parameter, because we don't know these things, right? We don't know the scale, the projection, the rotation. We don't know how somebody's head is in space with relationship to the camera. And we don't know how this person looks or what their expression is. But we have an idea of what the corner of an eye looks like. And we have an idea of how to represent this guy's appearance and expression with just 24 different values. So there's a sort of great big global searchy thing that goes through and starts adjusting all the various values in here. We're not even going to talk about this. That basically figures out, given this model, and they basically said both the trained point distribution model, this thing, and the landmark classifiers were provided to us by the authors. So basically, they used this guy's paper to figure out the 2D location of those points, which is really cool. Now, this is one way of doing it. And it is a machine learning kind of thing, because we built this matrix on a per point basis based on a whole bunch of input data. But this paper has been supplanted by the paper we covered in Chalk Talk about half a year ago. And quite frankly, this is under active research. It's all about facial detection. So there's lots of different ways of coming up with this list of points on somebody's face, and you can use whichever one you want. I thought this one was interesting because of the built-in sort of description of a face and its expression in just 24 different parameters here. All right, so kind of cool. We're not going to go much more into detail than that, because we're just going to give this one to whichever way you want to do it. And the best way to do it is dlib. Dlib, I don't know if it's dlib.com or dlib, but it has an open source version of this. It works quite well. The library dlib, you can just download it, shove an image at it, and it'll spit out the location of these red dots for you. Notice that in the paper's technique, they did have this basic three-dimensional idea of where the point is. We don't care about that because it's not accurate enough for us to use at this point. All right?
Actually, the version in dlib is the same one as they use in the paper.
Is it? Are you sure? I thought it was the one we did in Choctaw. Oh, I didn't even know that. Wow, okay, great, yay. So dlib's version was the same one in the paper.
Oh, for facial landmark detection.
Really? Are you sure? Okay, I believe Rashab is correct. Yes, it must be the same one. So yay, even better, just use dlib. Okay, now, here's the next thing. We're going to go to the next paragraph. This is section 5.2. The cool thing about this, and especially if you've ever used it, is that it works. It actually is fairly robust. dlib actually comes with a executable that you can build that attaches to your web camera. You can put it in front of your face, and all of a sudden you'll see these dots that follow the 68 points that it's tracking. But it's not super accurate. And remember, this paper is all about accuracy. How much detail can we get from the animation of this guy? So the next couple of steps that we're going to do is going to be trying to refine the accuracy of those points. So automatic keyframes section is next. Keyframes? What? So here's the thesis. There may be localization errors in the detected features, especially for expressions on which the tracker wasn't trained. So if you're doing a crazy expression that wasn't captured in that little matrix that I have here, yeah, it's like the points might start sliding off or not be in the exact right spot. This is a fairly robust feature tracker. When it doesn't work, it really doesn't work. It doesn't track any points, but when it can find your face, it usually gets the points close to the right location, but we want it better. To account for such errors, we correct the features locations using accurate optical flow between keyframes. So think about this. What we're going to do, and the whole idea is we've got a sequence of animation, right? We've got animation of this guy where he starts out in a neutral frame, and then he raises his eyebrow, maybe smiles, and he starts talking, blah, and so on. But, and we've seen this in other papers, with expressions, especially as you're moving your face and stuff, you always tend to return to a neutral pose. Let's get rid of that dot. So as you're talking, you eventually close your mouth, you come back to it, and you let your face rest as you are going through this. So the thought is, you know, these neutral poses that I have in my animation are pretty good to find. When I get to a neutral pose, my feature tracker really starts shining because the neutral pose is the easiest thing in the world to find. So when you start getting into crazier expressions, why don't we do this? Why don't we actually use optical flow, a different technique that basically tracks a point on a face here through time. It's going to follow that point as it goes through time in this animation. And we'll use the stuff that we're really sure of and then sort of warp or use this optical flow stuff to fix the things where we're probably pretty sure that there's going to be some errors. All right? But first of all, the very first thing is how do we find where the neutral poses happen? All right? So, get rid of this. Start writing over here because we don't need this. Step one, and this is a sub-step, appearance descriptor. I love this part. In fact, we've talked about something similar to this. So keyframes are selected by comparing the facial expression of each frame with the appearance of a reference frame that has well-localized features, such as a frame with a neutral pose. Okay, cool. All right, in our application, we assume that the starting frame, the very first frame in our sequence, is a rest pose. So that is one limitation right off the bat. In the future work part of this, they say, you know, this doesn't have to be, we could actually detect the rest pose, but it's super easy if we just have the actors start off in a rest pose. So if you're using this for web-based application, that's pretty much a bad assumption. You don't know what somebody's going to be doing when they start using this. But in this case, let's assume rest pose at the beginning. All right, we first align all the frames in the sequence to the first frame using a 2D affirmation or affine transformation that maps the best set of detected features on the reference, or the best set of detected features onto the reference shape. So think about that. We have a neutral pose at the very first frame, frame 0. And then somewhere over here, maybe this is frame 7, person is smiling and talking. So to make the optical flow a little bit easier, what we're going to do is take these features and try to align them as best as possible to this guy. So every frame is going to get an affine transformation that warps the frame so that it fits as best as possible to the neutral pose. Okay? Now, next, we consider, so back up a little bit. The paper is jumping ahead here. Why are we doing this? Well, you can kind of think of what we're going to be doing. We are looking for neutral poses, right? So what we're doing is taking the features that were detected using our fancy feature detector and taking this face and making it fit as close as possible to this face. That's not good enough. What we want to know is if this face and this face are very, very similar, like they are in the neutral pose. They will never be quite perfect, but how do you do that? Do you just subtract the faces? Well, that's not good, because lighting might change. There might be a lot of different reasons why just subtracting the faces isn't going to work. What we need is some way of comparing, once we've taken this face and squished it on top of this one, whether or not they're basically the same expression. So, next, we consider 3 rectangular regions of fixed size around the eyes and mouth. And they're basically using this, and other papers do this too, and some of the papers they reference. They basically say the eyes and the mouth are really good indicators of expression. So what we're looking for are eyes and mouths that are looking really close to each other. So what we're going to do is split them into several tiles for which the appearance is represented as a histogram of local binary patterns. This is so cool. So how do you compare 2 things? So here we go. We have an eye, and we have another eye. And maybe the lighting changed, but we want to know, are these guys close? Do they equal each other? Wow, if you're just a compositor, you'd say, well, okay, but these are these are little images, right? So there's pixels all over here. And again, just subtracting the pixels or taking the, subtracting them and squaring them and adding them all up, not the best way of doing this. What we want is more of an adaptive thing that they can handle a little bit of distortion, handle like maybe the eye is rotated a little bit. The pose of the face might be a little weird. How do we do that? Well, they use this thing called, make sure I get it, local binary patterns. Local binary patterns. This was really cool. So how do you compare, given the fact that lighting might change all sorts of stuff, whether something is the same? So now the concept is pretty easy. We're going to zoom in on that chunk. And we're going to do this for 1 pixel. So if we have a 3 by 3 image of pixels around a center point, we can go through there, and each one of these pixels has a, let's do it in grayscale, a value. So this might be 50, this might be 103, this might be 2, this might be 17, and so on. Each one of these pixels has a grayscale value, right? Well, what we can do is first convert this into a binary image, where we say, is the value here, 74, bigger than the center pixel? If the value is bigger than the center pixel, put a 1. If the value, let's call this 10, is less than the center pixel, put a 0. And we just go through here, we'll make up a number there. This one doesn't matter, I think they always make the 0 in the center. 0, 0, we'll go 1, and 0, whatever values we fit in there. All right, now we're going to take this and convert that into a number. So we're going to write this down as 0, 1, 1, 0, 0. I should have made an actual thing. We're going to convert that into a binary number by just taking the top row, the second row, and the third row and stretching them out like that. All right, now, who's good at binary numbers? What is that value? I have no idea. Maybe it's 217. It isn't because it's not on. Let's call it 218. Quick. That is a kind of description of what's going on in this neighborhood, right? The fact that this has a 218 isn't based on the values in here. It's based on the change, the absolute change, whether something is brighter or darker than this pixel. So it's a sort of compact representation. We've kind of compressed this thing down into it. Yeah, I've drawn this at a fairly low resolution, but remember that we're comparing whether this eye looks like that or this eye. So if we did this to every single one of these pixels, if we looked at the pixel and at each center point, we created a binary value for one of these, we could start putting that in a histogram. And the size of the histogram, the number of buckets in this histogram is going to be equal to the 2 to the number of pixels you're looking at, right? So this would be 2 to the, and actually you don't use the central one because it's always equal to each other. So 2 to the 8th would be the value there. So it's 64. So it would be 60. So this is wrong. Whatever this would be, and I'm missing a 0, so let's take that one. So whatever value this would be, we're going to put, actually 63 here. It's 2 to the 8th, 64. Yeah, 256, right? Of course. Don't know what was going on there. So we go through, and for every pixel in the eye, if this thing turns out to be 127, or 6, let's go. We find bucket number 126, and we add 1 to it. We put a value there. And if it's over here, we put a value here. And maybe there's another 126, or whatever. And what we're going to do is build a histogram of these descriptors, right? Might have a whole bunch of these guys. And we get a histogram of what this little descriptor is around this eye. Now they're getting this going, well, what? Why are we doing this? This is weird. All of a sudden you think, holy smokes, this is actually kind of cool. This thing is actually really a neat concept because it doesn't matter if the lighting changes. Remember, if the light bloomed or something, because the features are basically the same, you can kind of expect that these values are going to stay the same. And so this descriptor is going to be the same. And it turns out, if you start looking at this, this is actually fairly robust to translation and rotation. This histogram that you're building doesn't really care about a lot of stuff. It's basically saying, do I see patterns like this? And some of these values are going to be shifting and kind of moving, but eventually you're going to get sort of a wavy description of what your face looks like. And that wavy description of what that feature looks like, even if you rotate the eye, if you do some stuff like that, it doesn't change, which is really cool. One of the things that they do is they say, look what we're doing. We're kind of doing this in a circular way. Let's really run with that. So when you do a local binary pattern, if I've got an image, let's draw some more pixels here. Zoom, 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 zoom. And I'm curious about the local binary pattern around there. You can actually say, don't just use the 3 closest neighbors. You can actually do a circle. This makes it even more rotationally invariant, where you're going to now take samples that are evenly spaced around this pixel, or this circle that surrounds the pixel. And the distance of the pixel they usually refer to as L. So you can take these samples around here and use that to create your local binary descriptor of this pixel in the center. And if the pixels don't fit, or the sample points don't fit right in the center of a pixel, you can linearly interpolate them by the neighbors. So now you're really building in this kind of description of what's going on around this pixel into this. It doesn't really matter if this rotates, right? Because you can see if this whole image rotated around here, the way we're building this, you're going to get the exact same value out of there. How cool is that? It's a really clever way. So now, all you need to do is have a way of building a histogram like that for the neutral eye, and a histogram like that for the eye on a frame that you're in, and comparing them. Well, to compare them, there's this thing called a chi squared distance measure. And if you take one thing away from this thing that could be actually useful, because histograms start showing up a lot in image processing and all sorts of stuff, right? We deal with histograms, color histograms, all sorts of stuff. How do you compare histograms? Well, there's a couple of different ways, but this way is a fairly robust way of doing it. And it's actually relatively simple. It's just the sum, and then you can even weight. And I is the bucket in the histogram. So if you want to treat the histogram as exactly the same, one thing versus another, then W sub I can be 1. That's a default. And you take the bucket in one histogram and subtract it from the bucket in the other histogram, we'll call it Y, and square it, divided by xi plus yi. And this is the chi-squared, well, this gives you the chi-squared distance. So the smaller this value is, you've got to convince yourself about this. So the interesting thing about this is and there's one other thing. You have to normalize this histogram for this thing to behave correctly. So you have to make sure that the sum of all these values, and this just means that you sum up all the values that you've got in this histogram, and then you divide the height of each one of these guys, so the sum of the values always equals 1. So given this thing, and take a look at this little equation. I'm still working on the intuition behind this equation. But the paper and the Wikipedia articles on this say that this is a very robust way of comparing histograms to say whether or not one histogram is equal to another. And you kind of see it's based on the size of the height of these things. So I'm still getting an intuition on why that works, but it's supposed to be cool. All right. So what do we got? Back up a bit. First of all, we have a way of taking an I and determining whether it looks a lot like some other I, right? So we take this, create a patch around the eye. We know where the eyes are because we have a feature thing that has basically detected where the eyes are. Take a patch around it, compare it with another patch. And by the way, because we're doing it on a histogram basis, it doesn't really matter whether or not those patches, if the eye is the same size or anything, because even if the patch is a little bit bigger, the histogram is going to have the same kind of shape. So we're going to take this eye, compare it to this eye, and do it not only for the eyes, but for the eye, the mouth, and the smile at the same time. So we build a patch like this, then a patch for the other eye, so there's another eye back here, and a patch for the mouth. And we take each one of those histograms and string them together. So you actually have a histogram here for 256 for the first eye, another histogram, 256 for the second eye, and then another histogram, even bigger, let's call it 512, for the mouth. And we create this longer histogram that describes the entire face in a neutral pose. So we are then going through here and comparing each individual frame with this neutral pose histogram, and we're looking for things that produce the smallest value. So at the end of this, cool, you end up with a sequence of frames where you have a very good idea of where the neutral poses are. So, all right. And the idea is that when you get to a neutral pose, your feature detector is usually fairly accurate. And that is a big assumption, but according to their research, they've been happy with it. Okay, so now, all right, what do we got? Go back, we can get rid of all the local binary patterns. We have this way of doing this. So we have features, corners, eyes, the mouth, the nose, the on each one of these guys. and so on. There we go. And we know which one of these frames are neutral poses. So if we assume that we have a keyframe at time capital T, let's go for a different color here, then we compute the feature localizations at a later time. So x sub I, and x is the 2D location of these points on like that guy. At some time t is equal to a weighting parameter, x sub I f t plus 1 minus weighting parameter x sub o I t. All right. What? Ooh, let's put hats on this one. First of all, this isn't all that hard. This is what our feature detector said. So remember, let's say we're on the corner of an eye right here, and we're not trusting it. We're not so happy with it. It's not so good. So this guy is what the feature detector told us. Our fancy feature detector spit out something. But what we really want is a corrected version. So what we're going to do is blend the location that we got from the feature detector, which may or may not be right. There's going to be this blending value, this signal thingy here. What is that? Theta. Lambda. Thank you, lambda. Lambda times that. Well, what's that? Well, this is the location based on optical flow where x o t is equal to x sub t, and these should all have eyes on there. Sorry, the paper doesn't actually have it. Plus sum of t less than or equal to I less than t w sub I. Right, what? We're going to go through this. This is the location of the feature on the nearest neutral point, which we assume is pretty good. So say this is F7, and the nearest neutral frame is F0. So this is the location of the corner of the eye on this frame. And then for every frame between 0 and the frame that we're looking at, we're going to take the optical flow that is tracking that corner of the eye and move that point forward. So we're actually going to drive this location of this point forward with the optical flow motion that we get from analyzing these images, which is kind of cool, actually, right? And remember, what you're doing is optical flowing, but you're not only optical flowing. If the guy's moving his head in the image, that's a real pain. Then you have to optical flow the face. But remember, we did an affine transformation where we sort of aligned the faces as best we could. But you do the optical flow on the aligned faces so that the optical flow doesn't have to work as hard. And so this thing is basically saying, hey, from one frame to the next on this aligned frame, we can back out the alignment later. We're going to follow that point as it moves. So this is our feature detector telling us where it is. This is our optical flow thing that's flowed that point over. And in fact, they say, you know what? This is not the only thing that we do. This tells us to go forward in time. We actually go backwards in time too. We take, if this is frame 30, next neutral pose, we're going to take the corner of the eye here and flow it backwards so it gets to there. And we're going to take the corner of the eye and flow it forward so it gets to there. And average the two, or well, you weight the two based on how close you are to the neutral poses. So, they say it works. And in fact, they have tables and stuff that must mean that it works. But they were able to reduce the error of their feature detection by at least, it looks like around 50%. They're getting quite a reduction where after the correction, the features may have been up to 6 pixels away from where they wanted to be, but then after all this correction, they were on the order of 3 pixels away. So, you know, good improvement of stuff. All right. Cool stuff, right? I mean, this is interesting. And think about all the stuff they're doing just to figure this out. Because remember, all they have is one picture of this guy on a per frame basis. Okay, now, step next. So, and this was optical flow feature correction. So 5.3 optical flow. 6 is coarse expression and pose estimate. This is where it gets really fun. Estimation. Okay, so now we have, what do we have? We haven't even talked about our personalized blend shape really. But what we've got at this point is relatively vetted points on a person's face. We know where these 68 points are on this guy's face. So now the trick is, how do we align the 3D blend shape model to the 2D sparse features locations? How do we make it so that our blend shape actually fits where these points are? So they solve an optimization problem, of course. Step 1, 6.1, couple 2D to 3D. This one's actually pretty easy. So they take their personalized blend shape, put it in a neutral pose, render it. Actually, render this image. Render that image and run the feature detector on it. So we run this feature detector that gives us this thing. So there's our neutral, our blend shape thing. Let me do it in green because it's different. And we have the feature. Oh, well, I'm not going to do it in green. So now we do the exact same feature detector on this and create. We're basically asking the feature detector and say, let's pretend that this is an actual picture of a person. It isn't. It's the rendered blend shape model. But we're going to run the feature detector on it anyway and figure out what values it spits out. Which is clever, right? You don't want somebody identifying it. You want the feature detector. We're running this feature detector on every single frame of this image. We want to make sure that when we find a picture of a feature on this, it corresponds to the feature on our blend shape guy. Awesome. From this, since we rendered that point, we also know its 3D location on the image. On the model. So score. We now have a couple between the 2D location of where this sits in the image to the 3D point on the thing, which basically said, where do these features land on the model? Done. That was easy. Expression estimation. All right. Given a set of facial features, locations, these red dots, and estimated in the current frame, whatever frame we're on, a personalized blend shape model, this guy is called EBI, that is, given the blend shape weights and this model, you spit out a mesh. It is our task to estimate the current facial expression in terms of blending weights. So what we're going to do first, and I'll jump ahead here, is expression estimate first. And then 6.3, pose estimate. And wait, what? What's the difference? Remember, this is a photograph of somebody who's maybe holding a camera phone or having a single camera standing in front of it. You're going to move your head. So there's two things that can affect where these points lie in the image. Your expression and what you look like, and the way you're pointing towards the camera. So we need to solve for both of those. We're going to do this in an iterative fashion where we're going to figure out the expression first, then we're going to jump to the pose and back and forth and back and forth and back and forth. So hopefully we refine in on this cool thing. The neat thing is we have an estimate of what this guy's face looks like. Okay, so the expression transfer, and get ready for some crazy math, but we're going to take a look at this. Go through it slowly. Minimize based on the expressions for a given time, right? Sum over I of this monstrous thing. We're going to take S sub t, R sub t, E sub t, X sub I, t plus t sub t minus X, this is capital X, F, I, beta, J, and this is over J, there is this fine. Yeah. J, T. What? All right, we got to take a little bit of time here to think about this. So, what's going on? We have, this is a vector, and that's actually a vector, that's a great thing, and that's the face, right? So this are the coordinates of the feature vertices of the blend shape model, right? Which we knew about because we did this detection, right? So we know where the feature vertices of the blend shape model are, and these are the parameters that we're trying to figure out. We don't know BI, that's why we're going to be, this should be a J, sorry, oops. We're trying to figure out the best B's, the best values that, or betas that adjust our blend shape model so that this subtraction, as we sum up over all the features, all 68 features, is the smallest. Well, what's this? Well, if you remember from the sort of initial thing for detecting the features, these guys are the feature locations, right? Those are the red dots on the image, and these are 2D pixel things. But this is a 3D world coordinate. So somehow we have to take the 2D pixel thing and project it into a world coordinate. Well, okay, wait a sec, we have an idea. We have an estimate, we can come up with an initial estimate of a rotation, an initial estimate of a scale, an initial estimate of a translation. And this projection is a little weird because we don't know the camera parameters. How do we know what projection is? And when I first thought about this, because right, this is a monocular kind of thing, you can look at a point, but how do you know how far away it is? Well, they bailed. This was a really interesting part of the paper. Go orthographic. Go orthographic on the projection. And what's an orthographic projection? Well, that is a projection if you've got a camera. Here's our camera with an image plane. Here's our camera image plane. And I've got a point. You just go straight back. There's no, typically a camera has a projection like that. Now, orthographic is just straight back. It just takes every point and puts it parallel to the image plane. So what they're doing is taking this projection matrix, which does that, and an orthographic projection matrix looks like this. 1, 0, 0, 0, 1, 0. So if I multiply this by a 3D point, x, y, and z, you can see what's going to happen. The thing that spits out of here, remember we've got a three-dimensional point here, take this, multiply it by that, you get x. Take this, multiply it by that, you get y. That is your 2D location. Oh, wow. Look at this. We've taken a three-dimensional point, made it a 2D, and we just basically threw away the z. We don't, in typical perspective projection, you divide by the z and it gets all fancy and there's some neat stuff. Here we're just throwing away the z. Well, they're taking this projection matrix, turning it over, and multiplying the 2D point to get a 3D point. Well, the 2D point is basically going to be a 2D point with a z for 0. They're basically placing this thing on a plane at the 0 coordinate, and that is the representation of this space. And you're like, What? You can't do that. Think about what they're doing. I was freaking out when I read this. I was like, you can't do this. You've got a three-dimensional thing. You've got an image of a face, right? And you're doing a projection on a 3D. So you're creating a mesh of this face, and it's all centered around the origin. And it's a flat face. So this guy is just a flat face centered at the origin along the 0Z axis. But you're rotating it, and you're scaling it, and you're actually translating it. So you can actually take this and rotate it. So it's tilted a bit, right? So you can rotate, you can turn it this way, you can do, this is a full-on three-dimensional rotation. So you can actually skew that guy. And you can scale it, you can make it bigger, and you can translate it in 3D space. You can move it around, but it still stays flat. Do we care? No, because we'll get to the actual perspective projection in just a bit. But for now, this is the big assumption of this paper. It can work. So what we've done is think about what we've done, taken the 2D, 68 2D points, and basically converted into this 3D billboard that we can translate and rotate and move in space. Now what we're going to do is subtract the current blend shape model with this 3D thing. And in fact, they even throw away the Z when they do this. So we're doing it in a sort of, well, I don't think they throw away the Z at this step. I think they actually do the Z at one point, but in general, there's a thing that later on where they do throw away the Z. All right, we've got 1 minute left. Solving this is, this can be solved efficiently by methods based on sequential minimization, minimal optimization, Platt, 1998. So left as an exercise for the reader. Oh wait, I was right. As opposed to alignment step, we found experimentally that blending weight optimization is more robust if you performed only the X and Y coordinates. So this step, we discard the depth information. How cool is that? Now, once they've done this, the cool thing is you have blend shape parameters that have deformed the face so that it kind of aligns with your 2D image, right? You've done this. But the better that you can get this thing so that the rotations are right and the translations are right, the better the deformation of this face can be. So we then go through and do this again where we actually adjust the rotations and the parameters and the translation parameters to make this fit better. So the first thing we do is look for betas. Then the second thing we do is say, well, you know, the rotation thing of our billboard, let's see if we can get it to fit even better. So we go through and change those guys. Again, another minimal optimization. So we do expression estimation and then pose estimation. And finally, at the very, very end, we take our best blend shape values, which have taken our face that looks like this person, that made it look as much as like the expression as possible, and we throw it at basically a 3D tracking algorithm to say, all right, let's stop pretending this is an orthographic projection. Let's actually use this model and the 2D coordinates to actually figure out the actual pose of this guy. So we throw it at a standard 3D tracking algorithm that figures out the location and pose of that guy's face, which brings in the camera. So cool, and it actually works. Sort of. So what does this give you? It gives you a blend shape rig that is in a fairly good representation of this guy's expression, and they have examples in the paper about how this works, that's pointed in the right direction. So now we're over, and I don't know if I want to go back to this paper next time, but the next thing to do is to use optical flow again. And really, really quickly. It's kind of a clever algorithm. I told you this thing uses every trick in the book. So they use temporal optical flow to put in extra details. So what they want to do is get a dense expression. What this has done has gotten an expression that lines up with these 68 points. But we want to do it on every single frickin' point in the mesh that we have. So we want to make sure that all the points in the mesh line up with what we've seen there. How do we do that? Well, the cool thing is, they take their blend shape model and they color it. They take this blend shape model and have different colors all over the place. They basically create a very modeled version of this blend shape model. And because we now have an estimate of how this thing moves, they have a way of rendering this from one frame to the next with this modeled, really easily tracked blend shape grid. So you can create a sequence of frames that look like this guy's talking. Well, we also happen to have the actual sequence of frames of this guy talking. Well, let's start this way. So we have our blend shape that does this, that's modeled with all sorts of different colors. And we have our actual guy who's talking up here. So what we're going to do is do optical flow on this. We're going to have optical flow through here, which works great because of the great colors that we rendered it at. And we do optical flow on this, but not just on these 68 features, but through the whole image. We build a dense optical flow field which tells us how these pixels in here are moving from one frame to the next. And then, this is cool, for one frame, let's say t equals 11, and this is t equals 10, this is t equals 12, and say these all line up, they have a new optical flow algorithm that says, wait a second, let's try to figure out how these pixels move and link them up with how these pixels move. And basically figure out the deformation that we need to do to these pixels to make it look like what we actually saw in the image. We have so run out of time to talk about this, but this is a really clever idea. It's taking optical flow to the next level, where you're not just optical flowing one frame to the next, you're optical flowing 6 frames to the next. You're looking at this sort of matrix of frames and saying, how can we take this optical flow to fix this? And what you end up with is for every vertex in this mesh here, you have a little corrector that says, no, this thing moved like this in this image, but we really want it to move like this because this is what we actually filmed. We're going to use that to deform this face. And this puts in a whole bunch of extra detail. Was there time for questions? I don't remember there was time for questions. I think we're done, actually. We have to go. But, oh my God, oh, and there's one last step, by the way. This just puts in the whole detail. The one last step, might as well, because I see you're setting up for the next meeting. The last step is they put in even more detail by using shape from shading. And shape from shading basically says, look, if I know that this patch on this face renders to one way, and I see that patch on the face render to another way, we can adjust the normals. We can basically displace the image so that the shading works out to be exactly the same. And you can get even more details from this. Really clever. You don't even need the shape from shading. This second optical flow puts in a whole bunch of extra detail into this, the face. All from one frame, or one camera. How long does this take? It takes a while. Feature detection takes a couple of seconds per frame, the way they're doing it. And all this optical flow correction and all the high resolution details, 4 minutes a frame. I told you it wasn't real time at the very beginning. This is not real time whatsoever, but it could be sped up. This was 3 years ago. Computers are now 75 times faster. Bye, y'all. See you next week. No idea what we're going to be talking about next week. It'll be fun, though. Isn't that not cool?
That was super cool.
Super cool.
I'm the most interested in seeing the